All right, so if we've got a question like this, obviously we said we needed to do a few things. First off, we want to write down our givens. Okay, the givens for this question are that we know the distance that the force exerted, which is what we're looking for, so we can write the force as a question mark, but we know the distance over which it was exerted was decimal 23 meters, and the cart increases speed from 1.2 meters per second to 3.1 meters per second. And the mass of the car is 650 grams. What's wrong with that? It's not in kilograms. Okay? Mass always has to be in kilograms in physics, because otherwise we won't get kilogram meters squared per second squared, which are joules. Okay? So, if I want to convert 650 grams into kilograms, I divide by oh my gentle Jesus. Why? How come you guys don't know the metric system? 1,000! Thank you. Kilo means 1,000. That's the beauty of the metric system. It doesn't matter whether it's a kilometer, kilogram, kiloliter, kilonewton. It's always 1,000. See, that's the beauty of it. It's not like in the imperial system where you got to remember there's 12 inches in a foot, 3 feet in a yard, 16 ounces in a pound, or 8 ounces. I can't remember what it is. It's just too hard. It's too many different numbers. The metric system is beautiful. It's always easy. Okay, so we divide by 1,000. 0.650 kilograms. All right. What kind of energy is changing is the next question I'm supposed to look at here. So if I go back to the context of the question, okay, I've got a spring propelling a car, and it's increasing its speed. So what kind of energy is changing? Kinetic energy is changing. All right, so we go back to here, and we go that work is a change in kinetic energy. Work can be calculated by force times distance, and I'll have to use that because they didn't give me the work, and they're asking for force. And the change in kinetic energy means final kinetic energy minus initial kinetic energy. And I have both because I was moving at the beginning, or the cart was moving at the beginning, and it's moving at the end. All right, if I want to get force by itself, what do I have to do with D? Divide it over to the other side. Okay, then we plug in our numbers. So force will equal 1/2 times 0.650 times 3.1 squared minus 1/2 times 0.650 times 1.2 squared, all divided by 0.23 meters. All right, and when we're plugging that into our calculator, obviously the answer is right there. Okay, when we're plugging that into our calculator, we do have to be careful, okay, that we're doing one step at a time, okay, and kind of obeying order of operations and all that good stuff. So 0.5 times 0.650 times 3.1 squared. All right, so that's the first part. Now I got to subtract the initial kinetic energy, 0.5 times 0.650 times 1.2 squared. All right, so that's the top divided by 0.23 is 11.5 newtons. Okay, is that ringing a bell for everybody? Okay, as I see still a few people are struggling with this, and I think a lot of that has to do with manipulation. Okay, the algebra stuff. If you're struggling with the algebra stuff, then you got to get in and see me, okay, to work on your manipulation. Okay, remember, there's only 2.5 rules. If I want to move something, I do the opposite. So if I'm adding, I subtract. If I'm multiplying, I divide. Okay, if I do something to one side, I do it to the other. And I move what's not attached first. That's the half rule. Okay, everybody follow me there. All right. You have in front of you now a worksheet that's got work energy theorem problems on it. Your quiz tomorrow will have questions just like that on it. The quiz tomorrow determines whether you can move on from this stuff or not. I would imagine you're probably getting sick of it. So, do this worksheet, okay? Practice it up. If there's any questions, let's go through them together, okay? That way we can do good on the quiz tomorrow and move on to something else. All right, so we're not doing work energy theorem for 2 full weeks. Agreed? All right, so let's get to work on that one, okay, and I'll go through any ones that give you trouble with you. Okay, let's have a quick look at number 2 here, guys, just as a matter of wording. Okay, anytime I ask you what work is, you tell me it is or a change in energy. It's either force times distance or it's a change in energy. So the wording of this question sometimes gives people trouble. An object gains 155 joules of potential energy. Does that mean your potential energy changed if you gained some? So 155 joules is the work. Right? It's the change in energy of that box. If it gained 155, it's because 155 joules worth of work was done on it. Right? So we write in here in our givens that the work was 155 joules, okay? And it was lifted 1.20 meters. So does that, what variable is that? The 1.2 meters? Distance, yeah. All right, well, if I know work, distance, and I'm asked to calculate force, that's a pretty easy calculation. Work equals force times distance. So work over distance equals force. 155 over 1.2 should give us our 129.1 newtons worth of force. All right, so it's a matter of reading the questions carefully. It's not always going to say the change in energy is this many joules. It's not going to say that every time. Okay, sometimes you have to read the question carefully and go, oh, a gain means a change, a loss means a change, okay, things like that. Okay, let's have a look at number 3 here, guys. So, person stands on the gym floor and jumps up, straight up, to dunk a basketball. What kind of energy are they changing? Not if they're jumping straight up, they're changing potential energy if they're jumping straight up, not kinetic. Okay, they're not changing their speed. Does it ever mention any speeds in here? Okay, and the question asks us for how high did they jump? Well, that's part of potential energy. Right? So here's what we've got. We've got mass, 70 kilograms. Okay, and we've got that they gained 800 joules of energy. If you gained 800 joules of energy, what has been done? Work. How much work? 800 joules, because work is a change in energy. And if you gained 800 joules, that's how much work was done. The only way you can gain 800 joules of energy is to have 800 joules of work done. Okay? All right, so we know that, and of course we always know G. Okay? G is always 9.81 meters per second squared. Okay, so work is a change in potential energy. I'm not going to put in force times distance because I already know what work equals. Okay, and I'm not looking for force or distance, so I don't need to. Okay, what I'm going to write over here, though, is m times g times h final, the formula for potential energy, minus m times g times h initial. Now, since he jumps from the floor, how much energy would he have standing on the floor? 0. Okay, he's got no potential energy while standing on the floor. So we're left with work equals m times g times hf. How do I get hf by itself? Divide mg. First rule of algebra. If I want to move something, I do the opposite. Right now, I'm multiplying those 3 things together. Okay, so I divide by the 2 things I want to move, and I leave hf where it is. Then what I do to one side, I do to the other. Okay, divide by mg. Now, when you're punching this into your calculator, this is the trick. You can't just go 800 divided by 70 times 9.81. You have to go 800 divided by what 70 times 9.81 equals. Okay, that way you will get the right answer. All right, and that should come out to 1.16 meters. Everybody follow? Okay, I think we're struggling with the algebra a little bit here from what I see. Okay, so we got to work on that a little bit. You only need to remember those 2 things, guys. Okay? Move it, do the opposite, do it to both sides. Okay, for number 5, guys. Okay, we're having a little bit of an issue here. It's a units issue. Distance must be in meters. This is in centimeters. You can't plug in 10 into this question or you're going to get an answer that is 100 times too big. Okay? So you need to convert it to meters. All right, 0.1 meters. Okay, so on number 6 here, we are given the mass of the rubber band. Okay, 0.02 kilograms. Okay, and the rubber band has 320 joules of kinetic energy. So they tell us it's EK. Okay, how fast is the rubber band going? So I'm looking for V. So is this the formula for kinetic energy? Right? There's no initial and final here. We already did the work part. Okay, that was up here. Now they're just asking us, it has this much energy. How fast is it going? It never said work, right? It said it has this much kinetic energy. Here's this mass. Find out how fast it's going. So all I have to do is manipulate for V. So I divide both sides by half of m. Okay, everyone follow me so far? And then I don't want V squared, I want normal V. So I've got to square root both sides. So when I square root 320 divided by half of 0.02, I get a ridiculously large number. 178.9 meters per second. You would most certainly lose an eye if it was going that fast. Okay? Okay. Other ones giving us trouble. All right, let's keep going. There, you guys see in here now how important it is to read the question carefully. It's all about the wording. Okay? If it says, you know, work or there's a change in energy, then you know it's work. But this time it just says all of it's kinetic. So that just means it's straight kinetic energy. It has nothing to do with a change. That's just how much it has. All right? Okay, let's have a look at number 7 here, guys. Listening, please. Force of 100 newtons. And guys, this is the exact example I gave when we did the lesson there last week. Okay, was the bow and arrow. Force is 100 newtons. Okay, it draws a bow back a distance of 0.29 meters. At what speed will a 0.120 kilogram arrow leave the bow? All right, what kind of energy am I changing here? Kinetic. I mean, yes, I'm changing the elastic potential energy of the bow, but they never ask me about the bow. They only ask me about the arrow. Now, when the arrow is in the bow, how much kinetic energy does it have? 0. Because it's sitting there. It's not moving. It's just in the bow. All right, so we're going to set this up same as we always do. Work is a change in kinetic energy because we've identified that we're dealing with speed. That has to do with kinetic energy. Force times distance equals 1/2 mvf squared, the final speed. So this is our final kinetic energy, subtracting our initial kinetic energy, which we just said is what? Is 0. All right, so we're going to get rid of that. So force times distance equals 1/2 mvf squared. How do I get vf by itself? Divide by half of m. All right, and then what do I do? Square root. That gets rid of the square. Now I can plug in my numbers. 100 times times 0.29 divided by 1/2 times 0.120. And when I do that, I should get 22 meters per second. Okay, that is exactly like what will be on your quiz tomorrow and your unit exam on June 3rd. Okay, that is a stereotypical work energy theorem question. Okay, and the other one's giving us trouble. 10. All right, so Sam goes into this plane. He flies to a height of 1,250 meters. Okay, so we know his initial height is 1,250 meters. He has a mass of 55 kilograms. How much potential energy does he have? that the formula for potential energy? This didn't ask about work in any way, did it? Never gave us force, never gave us distance, just asked about potential energy, period. All right, so EP equals m times g times h. 55 times 9.81 times 1,250. Okay, now that's going to give us 674, and then there's a few other numbers, but I rounded it off because there were so many. What was it? 57.5. Okay, so if I have 6.74 times 10 to the 5, what I've done is I've put that in scientific notation just to make it smaller. All right, so I've moved the decimal 1, 2, 3, 4, 5 spots. 10 to the 5. Okay, so it's just in scientific notation. If you got this number here, you did it right. Okay, yeah. Any other ones? All right, keep going. I'll post tomorrow's quiz later on today, guys.